Imagine living in a country where rain is so rare that an entire year's rainfall can disappear in a single hot afternoon. A place where rivers don't flow, lakes don't refill, and underground water that took thousands of years to form is being drained faster than nature can ever replace it. This is the reality Saudi Arabia has faced for decades. Beneath the towering skylines and futuristic mega projects lies one of the most severe water challenges on Earth, a challenge that quietly threatened the nation's survival long before oil wealth captured global attention. Saudi Arabia sits at the heart of one of the driest regions on the planet. More than 90% of its land is desert, and most of it receives less than 4 inches of rain per year. There are no permanent rivers, no natural freshwater lakes, and no dependable seasonal rainfall to rely on. For centuries, people survived using small wells, oases, and limited groundwater, carefully rationing every drop. But the modern era changed everything. As cities expanded, populations grew, and living standards rose, water demand exploded at a pace never seen before. In just a few decades, Saudi Arabia transformed from a largely rural society into a highly urbanized nation. Cities like Riyadh grew from small desert towns into massive metropolitan centers with millions of residents. With growth came homes, hospitals, industries, and agriculture, all requiring vast amounts of water. At first, the country turned to underground fossil aquifers, ancient water reserves trapped deep beneath the desert, formed during wetter periods thousands of years ago. These aquifers seemed endless, but they weren't. The more water was pumped, the faster levels dropped, and unlike rain-fed systems, these reserves could not naturally recharge. By the late 20th century, warning signs became impossible to ignore. Wells had to be drilled deeper each year. Some regions saw groundwater levels fall by hundreds of meters. Agricultural projects that once symbolized self-sufficiency began to collapse as water costs soared. Scientists and policymakers realized a hard truth. Saudi Arabia was running out of fresh water, and there was no natural backup plan. Without decisive action, cities would face shortages, food production would suffer, and long-term national development would stall. This is where the crisis forced a radical shift in thinking. If fresh water could not be found on land, it would have to come from somewhere else. And surrounding Saudi Arabia on both sides was an enormous, seemingly infinite source, the sea. The Red Sea to the west and the Arabian Gulf to the east held trillions upon trillions of liters of water. The problem was obvious. Seawater isn't drinkable. It's corrosive, salty, and deadly to crops and human health. Turning it into fresh water at a national scale sounded almost impossible, especially in a harsh desert environment. Yet necessity has a way of pushing boundaries. What began as small-scale experiments soon turned into a national strategy. Desalination was no longer just an option. It became a matter of survival. Saudi Arabia didn't simply need water for a few coastal cities. It needed to move massive volumes of fresh water hundreds of kilometers inland, across scorching deserts and over rugged terrain, to reach places like Riyadh that sit far from the sea. The challenge wasn't just making fresh water, but delivering it reliably every single day to millions of people. The urgency of the situation reshaped national priorities. Water security became as critical as energy security. Massive investments were approved, new technologies were adopted, and long-term planning focused on one goal, ensuring that taps never run dry, even in the heart of the desert. This wasn't about luxury or convenience. It was about keeping cities alive, economies running, and society stable in one of the world's most unforgiving climates. What makes this story remarkable is not just the scale of the problem, but the boldness of the response. Instead of accepting limits imposed by geography, Saudi Arabia chose to engineer its way out of a natural constraint that had defined deserts for millennia. The decision to bring the ocean inland marked the beginning of one of the most ambitious water projects in human history, a project that would rely on cutting-edge technology, colossal infrastructure, and an unrelenting flow of energy. And this was only the beginning of how a desert nation decided to make the sea its lifeline. Turning seawater into fresh drinking water sounds simple when said out loud, but in reality, it is one of the most complex industrial processes ever scaled by a nation. Seawater is packed with salt, minerals, microorganisms, and corrosive elements that make it completely unsafe for human use. To make it drinkable, all of that has to be removed with extreme precision. Saudi Arabia didn't just adopt desalination. It transformed it into a massive, non-stop operation capable of supplying water to an entire country that depends on it every single day. At the heart of this system are enormous desalination plants stretching along the Red Sea and the Arabian Gulf. These are not small facilities quietly operating in the background. They are industrial giants, some of the largest on Earth, designed to process millions of cubic meters of seawater daily. Intake pipes pull seawater directly from the ocean, filtering out debris, sand, and marine life before the real work begins. From there, the water enters a tightly controlled environment where science, engineering, and energy converge. Two primary technologies power this transformation. One relies on heat and the other on pressure. In thermal desalination, seawater is heated until it evaporates, leaving salt behind. The vapor is then condensed back into liquid form as fresh water. This method is incredibly reliable and well suited for large-scale production, especially in a country with abundant energy resources. The second method, reverse osmosis, uses powerful pumps to force seawater through ultra-fine membranes. These membranes allow water molecules to pass through while blocking salt and impurities. What emerges on the other side is clean, drinkable water. Saudi Arabia operates both systems at a scale unmatched anywhere else in the world. Entire coastal zones are dedicated to desalination complexes, where plant after plant runs around the clock. Every hour, billions of liters of seawater are transformed into fresh water, carefully tested, treated, and prepared for distribution. Sensors monitor salinity levels, temperature, pressure, and quality in real time, ensuring the water meets strict safety standards before it ever leaves the facility. But producing fresh water is only part of the challenge. Desalination is energy intensive, and running these plants requires enormous power. High-pressure pumps, heating systems, and continuous filtration all consume vast amounts of electricity. For decades, Saudi Arabia leveraged its oil and gas resources to fuel this process, turning energy wealth into water security. Power plants are often built directly alongside desalination facilities, forming integrated systems where energy and water production are tightly linked. Over time, efficiency became just as important as capacity. Engineers refined membrane technology, improved heat recovery systems, and reduced energy losses wherever possible. Each percentage point of efficiency gained translated into millions of liters of water produced at lower cost. Automation and digital control systems now manage much of the process, allowing plants to respond instantly to changes in demand or operating conditions. What makes this system even more remarkable is its reliability. Desalination plants do not depend on rainfall, seasons, or climate patterns. Whether it is summer or winter, drought or heat wave, the plants continue to run. This consistency is what allows inland cities, industries, and communities to function without fear of sudden water shortages. In a region where natural freshwater sources are unpredictable or non-existent, desalination provides stability in an unstable environment. Environmental concerns, however, add another layer of complexity. Removing salt from seawater leaves behind highly concentrated brine, which must be safely returned to the ocean without damaging marine ecosystems. Saudi Arabia has invested heavily in diffusion systems and environmental monitoring to manage this process responsibly. Research continues into reducing salinity levels and finding productive uses for byproducts, turning waste into potential resources. The scale of Saudi Arabia's desalination effort has quietly redefined what is possible. What was once an expensive experimental technology has become the backbone of national survival. Entire cities now depend on water that was, just hours earlier, part of the sea. Homes, hospitals, mosques, farms, and factories all rely on a process that never stops, even for a moment. This transformation did more than solve a water shortage. It proved that with enough commitment, technology, and vision, even the harshest natural limitations can be challenged. The sea, once a barrier separating land from water, became a solution flowing through pipes and pumps, sustaining life deep in the desert. And from these coastal plants, the journey of that water was only just beginning. Producing vast amounts of fresh water is only half the battle. Once that water is created along the coast, it still has to reach the heart of the country, and that is where one of the most extraordinary engineering feats begins. From the shoreline, the journey inland stretches across hundreds of kilometers of open desert, rugged plateaus, and extreme terrain that pushes infrastructure to its limits. Moving water through this landscape is not a simple matter of letting it flow downhill. In many cases, the water must be forced upward, across elevations that defy gravity itself. To make this possible, Saudi Arabia built a network of giant pipelines unlike anything seen before. These pipelines are massive steel arteries, some wide enough for a person to stand inside, designed to carry billions of liters of water every single day. They run continuously from coastal desalination plants toward inland cities, buried beneath sand, exposed to scorching sun, and engineered to endure decades of relentless stress. Every kilometer of pipe represents careful planning, material science, and precision construction. The desert is an unforgiving place for infrastructure. Daytime temperatures can soar above 50 degrees Celsius, while nights can cool rapidly, causing expansion and contraction that weakens materials over time. Sandstorms can bury pipelines, expose them, or grind surfaces with abrasive force. To survive this environment, the pipes are built from specially treated steel, coated with advanced anti-corrosion layers, and reinforced to handle internal pressure far greater than that of ordinary water systems. These are not passive pipelines, they are active systems designed to fight back against nature. Pumping stations placed along the route act as the beating heart of this network. These facilities push water forward with immense force, maintaining pressure across long distances. Some stations are so powerful, they resemble industrial power plants, more than simple water facilities. They operate continuously, synchronized with one another, ensuring that water moves smoothly from one end of the country to the other without interruption. A single failure could affect millions of people, which is why redundancy, monitoring, and rapid response systems are built into every layer. In many sections, the pipelines must climb over high terrain, moving water uphill across mountains and plateaus before allowing it to descend towards cities like Riyadh. This is one of the most energy-demanding parts of the system. Pumps must overcome gravity itself, lifting water hundreds of meters above sea level. The fact that fresh water can be pushed from sea level to deep inland capitals is a testament to the sheer scale of engineering involved. It is not just transportation, it is controlled force applied with scientific accuracy. Monitoring systems track pressure, flow rate, temperature, and structural integrity in real time. Sensors detect even the smallest irregularities, allowing engineers to respond before problems escalate. Maintenance crews operate around the clock, often in remote desert locations, ensuring the system remains intact. Leaks, corrosion, or pressure drops are treated as critical threats because water in this system is not just a utility, it is lifeline infrastructure. The scale of this pipeline network becomes even more impressive when considering its reach. It does not serve a single city or region. It connects multiple desalination plants to multiple inland destinations, forming a web of water movement across the country. This flexibility allows water to be rerouted when demand shifts or when maintenance is required, ensuring uninterrupted supply even under extreme conditions. Beyond engineering, there is a strategic dimension to this system. By controlling water distribution through pipelines, Saudi Arabia gains resilience against drought, climate variation, and population growth. Cities can expand without needing local water sources. Industries can operate far from the coast. Even religious pilgrimage seasons, when millions arrive at once, can be supported with confidence that water demand will be met. All of this happens largely out of sight. Beneath the sand, beyond the highways, and across vast empty spaces, water is constantly on the move. It flows through steel veins that stretch farther than many people ever travel, quietly sustaining daily life in places that would otherwise be uninhabitable. The desert may appear unchanged on the surface, but below it, a river made by human hands is always flowing. And once that water reaches its destination, another powerful system takes over to keep it moving. Moving billions of liters of water across a desert does not happen quietly or cheaply. Behind every drop flowing through those pipelines is an immense demand for energy, applied with precision and consistency. Water does not move itself over hundreds of kilometers or climb mountains on its own. It must be pushed, lifted, and controlled every second of the day. This is where energy becomes just as vital as engineering, turning fuel and electricity into motion, pressure, and reliability. For decades, Saudi Arabia relied on its most abundant resource to power this system. Oil and gas fueled massive power plants that supplied electricity directly to desalination facilities and pumping stations. These were not distant energy sources connected by long transmission lines. In many cases, power generation and water production were physically integrated, forming tightly linked complexes where energy could be converted into fresh water with minimal loss. This integration allowed operations to run non-stop, day and night, regardless of weather or season. The scale of energy consumption is difficult to comprehend. High-pressure pumps must force water through membranes or lift it across elevations, requiring enormous electrical output. Thermal desalination plants demand sustained heat to boil seawater continuously. Pumping stations along inland routes consume power equivalent to small cities. Every decision about energy efficiency directly affects how much water can be delivered and at what cost. A slight improvement in pump performance or pressure control can translate into millions of liters saved or moved more efficiently. As demand grew, so did the need for smarter systems. Engineers introduced advanced control technologies that adjust pump speed, pressure, and flow based on real-time conditions. Instead of running at full power constantly, systems now adapt dynamically, reducing energy waste and wear on equipment. Artificial intelligence and predictive analytics are increasingly used to anticipate maintenance needs, detect inefficiencies, and optimize operations before problems occur. Energy is no longer just consumed, it is carefully managed. At the same time, long-term sustainability became impossible to ignore. Relying entirely on fossil fuels for water security posed economic and environmental challenges. Recognizing this, Saudi Arabia began shifting toward a more diversified energy mix. Solar power, in particular, emerged as a powerful ally. With vast desert landscapes and intense sunlight, solar energy offers a natural fit for water infrastructure. Large-scale solar farms are now being integrated into desalination and pumping systems, offsetting energy demands and reducing emissions. This transition is not symbolic. Solar-powered desalination projects are already demonstrating the ability to produce freshwater at lower long-term costs while minimizing environmental impact. Hybrid systems combine traditional power sources with renewables, ensuring reliability while steadily reducing dependence on oil and gas. The goal is not just to keep water flowing today, but to ensure that future generations can sustain the system without exhausting resources. Energy storage and grid integration also play a critical role. Water demand does not pause at night, and pipelines cannot simply shut down when the sun sets. Battery systems, grid balancing, and energy management technologies ensure continuous operation even when renewable output fluctuates. This complexity adds another layer to an already intricate system, where energy, water, and technology must operate in perfect coordination. What makes this effort remarkable is how energy has been transformed into a strategic tool rather than a limiting factor. Instead of viewing high energy demand as a barrier, Saudi Arabia has used its resources to build resilience. The same energy wealth that once fueled rapid development now powers the infrastructure that sustains it. Water security, energy security, and national stability are tightly interwoven, each reinforcing the other. This approach also influences global thinking. As water scarcity becomes a growing concern worldwide, the question of how to power large-scale desalination looms large. Saudi Arabia's experience shows that energy challenges can be addressed through integration, innovation, and long-term planning. It is not just about having resources, but about using them intelligently to solve problems that once seemed insurmountable. Every time a pump activates, every time pressure is adjusted, and every time water climbs another elevation, energy is being transformed into survival. The desert may be vast and unforgiving, but through controlled power and relentless innovation, water continues its journey inland, unstoppable and precise. And that journey ultimately leads to the cities, industries, and lives that depend on it. When that water finally arrives after its long journey from the sea, its impact is felt everywhere at once. It flows into homes, towers, hospitals, factories, and places of worship, quietly sustaining a society that could not exist in this form without it. Cities rise from the desert not because rain allows them to, but because engineered water makes them possible. In places where natural freshwater is nearly non-existent, this supply becomes the foundation of daily life. Riyadh is perhaps the clearest example. Sitting deep inland, far from any coastline, the city has grown into a sprawling metropolis of millions. Every glass of water, every shower, every green space depends on desalinated seawater delivered through pipelines stretching across the country. Without this system, Riyadh simply could not function at its current scale. The same is true for many other urban centers, each relying on a steady, predictable flow to support growing populations and modern living standards. Beyond residential life, industry depends heavily on this water network. Manufacturing, energy production, refining, and construction all require consistent water supply. Even small interruptions could disrupt operations worth billions of dollars. Desalinated water ensures that economic activity is not constrained by geography, allowing industrial zones to operate far from natural water sources. This flexibility has been a key factor in national development, enabling growth where it would otherwise be impossible. Agriculture, once a major strain on limited groundwater, has also been reshaped by this system. While water-intensive farming has been reduced in some areas to protect resources, controlled water supply still supports strategic agriculture, food processing, and livestock operations. By managing where and how water is used, the country balances food security with long-term sustainability. Every liter is accounted for, measured, and directed where it provides the greatest value. Religious and cultural life also depends on this infrastructure. During pilgrimage seasons, millions of visitors arrive in cities like Mecca and Medina, dramatically increasing water demand in a very short time. The system is designed to absorb these spikes without failure, delivering enough water for drinking, sanitation, and services on a massive scale. This reliability ensures that some of the largest annual human gatherings on Earth can take place safely in an otherwise arid environment. Looking toward the future, water plays a central role in national transformation plans. Vision 2030 is not just about economic diversification or futuristic architecture. It is about creating livable, sustainable communities. Mega projects like NEOM are being built with water efficiency, smart distribution, and advanced recycling at their core. These developments rely on the same desalination backbone, enhanced with next-generation technology to support ambitious goals without repeating past mistakes. Tourism, another pillar of future growth, also depends on water security. Resorts, entertainment districts, and coastal developments require reliable supply to meet international standards. Visitors expect comfort, cleanliness, and sustainability, all of which depend on a hidden but powerful water infrastructure. The success of these projects hinges on the ability to deliver water seamlessly, regardless of location or climate. What ties all of this together is planning. Water is not treated as an afterthought or a local issue. It is planned at a national scale, coordinated across regions, sectors, and future timelines. Demand forecasting, infrastructure expansion, and efficiency improvements are all part of a long-term strategy designed to support decades of growth. This approach transforms water from a limiting factor into an enabler of ambition. Perhaps the most striking aspect is how invisible this system remains to those who depend on it. Faucets turn on, cities glow at night, and life continues as if water were always abundant. Yet beneath the surface, a vast network works relentlessly to maintain that illusion. Pipes, pumps, plants, and power systems operate in harmony, delivering something so basic that its absence would instantly bring everything to a halt. This water does more than quench thirst. It supports dreams of modern cities, economic resilience, and global relevance in a land where nature alone could never provide it. It allows a desert nation to think beyond survival and focus on transformation. And all of it depends on ensuring this lifeline remains strong for generations to come. The system that brings water from the sea into the heart of the desert is already one of the most advanced on Earth, but it is far from finished. As powerful as it is today, the future demands even more. Climate pressures, population growth, and global responsibility are forcing a new phase of thinking, one that goes beyond scale and focuses on sustainability, intelligence, and long-term balance. The goal is no longer just to make water available, but to make it smarter, cleaner, and more resilient than ever before. One of the biggest shifts is happening in how energy and water work together. Traditional desalination proved what was possible, but the next generation aims to reduce environmental impact while maintaining reliability. Solar-powered desalination is moving from concept to reality, using abundant sunlight to offset energy demands that once relied heavily on fossil fuels. Large-scale solar fields paired with desalination plants are designed to operate efficiently in desert conditions, turning heat and light into a steady flow of freshwater with a far smaller carbon footprint. Artificial intelligence is becoming the quiet conductor of this vast system. AI-driven platforms analyze data from thousands of sensors across plants, pipelines, and pumping stations. They predict maintenance needs before failures occur, optimize energy use in real time, and adjust water flows based on demand patterns. Instead of reacting to problems, the system anticipates them. This shift from reactive to predictive management increases efficiency, extends infrastructure life, and reduces costs across the entire network. Water reuse and recycling are also gaining importance. Treated wastewater is no longer seen as waste, but as a valuable resource. Advanced purification techniques allow water to be reused for industrial processes, irrigation, and even reintroduced into potable systems under strict standards. This reduces pressure on desalination plants and creates a more circular water economy, where every drop is used to its fullest potential. Environmental protection remains a critical challenge, especially when it comes to the oceans. Managing brine discharge responsibly is a major focus of ongoing research. New diffusion methods, mineral extraction techniques, and alternative disposal strategies aim to minimize harm to marine ecosystems. Some projects explore recovering valuable minerals from brine, transforming an environmental concern into an economic opportunity. The sea is no longer just a source of water, but part of a system that must be preserved and respected. This evolving approach has implications far beyond national borders. As water scarcity intensifies globally, many countries face challenges similar to those Saudi Arabia confronted decades ago. The solutions being developed today offer a blueprint for others, especially arid and rapidly growing regions. Technology, policy, and infrastructure lessons learned here are increasingly shared through international partnerships, positioning this system as a model rather than an exception. Resilience is another key focus. Future systems are being designed to withstand disruptions, whether from extreme weather, technical failures, or geopolitical uncertainty. Redundant pipelines, diversified energy sources, and decentralized production ensure that water supply remains stable even under stress. This resilience is essential in a world where climate patterns are becoming more unpredictable and infrastructure must adapt quickly. Education and workforce development also play a role. Operating such advanced systems requires skilled engineers, technicians, and researchers. Investment in training ensures that local expertise grows alongside technology. This human element is just as important as machinery, because innovation depends on people who understand, improve, and safeguard these systems every day. Perhaps the most profound change is philosophical. Water is no longer treated as an infinite resource made available through wealth or technology alone. It is managed with an understanding of limits, responsibilities, and future needs. Every upgrade, every policy, and every innovation reflects a commitment to sustainability rather than short-term gain. The desert has not changed its nature. Rain remains scarce, rivers still do not flow, and groundwater remains precious. What has changed is humanity's response. Through foresight, investment, and relentless innovation, a system has been built that turns challenge into opportunity and scarcity into stability. And in doing so, a desert nation has shown the world that even the harshest environments can sustain life when vision meets engineering.